Good.
Okay, we're back. We were talking about roots and powers in the complex plane. We remember do Moivre's theorem, which is cosine x plus I sine x, in parentheses to the n is cosine nx plus I sine nx. But a really interesting and useful thing is to remember that we can write, this one's not good, we can write complex numbers like this. Z, which is a plus ib, this is the same as r e to the I theta, where r is the norm of z, which is the square root of a squared plus b squared, and theta is equal to the arctangent of b divided by a, if a is not 0, of course. If a is 0, it's obviously straight up or straight down. You should be able to, if b is positive, it's 90 degrees. If it's negative, it's 270 degrees, or 3 pi over 2. Okay, another thing, because sine and cosine, so this is actually r e to the I theta is equal to r times cosine theta plus I sine theta. But we know that cosine and sine are periodic with period 2 pi, so this is still equal to r e to the I theta plus 2k pi, parentheses, because I has to hit everything, where k is an integer, and this is of course the same as r cosine theta plus 2k pi plus I sine theta plus 2k pi. And so why is this nifty? Well, in particular, if we want to take roots, suppose we have z, which is equal to r e to the I theta, and we'll run theta as theta plus 2k pi. If we do this, suppose we want to know what the nth root of z is. Well, then that's the nth root of this. This is r to the 1 over n, and bringing this inside, we have, this is e to the I theta plus 2k pi divided by n. This is, and I'm just going on and on here, aren't I? Cosine 1, or r to the 1 over n cosine theta plus 2k pi divided by n plus I sine theta plus 2k pi divided by n. And k runs through 0, 1, to n minus 1, because once k hits n, the whole thing cycles again. You don't get anything new out of it. Okay, this is really wonderful and important. One of the things they're going to ask you to do is find the nth root of 1. And what does that mean? They're going to want to know, like, what's the third root of 1? So first off, suppose we have z is equal to 1. What's the third root of both of these? Well, we need to be a little more careful when we're going to do this. So now remember, the t-shirt of disgust was actually thrown away by the janitor, so now we have the t-shirt of semi-disgust. Hello, I hope you're having a good day. And there's this groovy stuff here. Hopefully this will stay in your brain, because it is totally groovy. But let's work on these roots of unity, it's called. Incidentally, the roots of unity, all of them lie on the unit circle in the plane. I guess I'll take all this down. We'll need all the room. And let's carefully think about this a little bit. And I've been using green. So if z is equal to 1, this is really 1 plus 0i. This is then the norm of z, which is equal to 1 squared plus 0 squared square root is equal to 1, which is equal to r. The whole point that I did this is because I want to write this as r e to the I theta. R is just 1, so I get to use e to the I theta. So, but we can write this as e to the I theta plus 2k pi, right? So this is z is equal to 1. I want to find, well, okay, so first off, what's theta? Let's be more careful. So here's the x-axis, or the real axis. Here's the y-I axis, or the imaginary axis. Here's some markings to make this look good. Here is 1, or our good friend 1 plus 0i. We're just laying it down right here. How many radians is this? This is 0 radians. It's just laying flat, right? So this is really 0, and that means we can write this as ei to the 2k pi is equal to 1. Now I want to find the nth roots of 1, and somebody's probably going, what are you talking about, the nth roots of 1? I mean, in real numbers, the square root of 1 is 1, the third root of 1 is 1, the fourth root of 1 is 1, and these are all bad notations. It'd be better to write it like this: 1/2, 1/3, 1/4. Why would this be any different? And let's see. Okay, so we know from de Moivre's theorem, which I'll never say right. I don't think I've ever heard it said right. I've probably never said right. We know that if we do this, the 1 over n, we're finding the nth root. So we have e to the I 2k pi divided by n is equal to 1 to the 1 over n. But this is the same as, I think I'm going to bring it up here, and then I'll work back down after I erase. This is the same as cosine 2k pi over n plus I sine 2k pi over n, where k is an integer and is equal to 0, 1, 2, blah, 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 n minus 1. It goes to 1 less than n. So this is the general formula for the nth root of 1. Let's work it a little bit. And I don't know why. Taking the general roots, I mean, this is just a specific case of the general root formula, which you should know. But people are really obsessed with the nth roots of 1 for some reason. I guess I don't know why, outside that it's kind of neat. Okay, so let's just do some of these and see what we end up with here. Let's see what the square root of 1 is. Okay. So in this case, I want the square root of 1, so I'm looking for 1 to the 1/2. I'm just going to use this formula. I'm not going to keep writing everything down. Okay, so let's just follow this formula. This is for k equals 0. This is going to be cosine of 2 times k is 0 over 2. So I'll write the 2 in here, even though 0 divided by 2 is 0, plus I sine 0 divided by 2. This is the same as cosine 0 plus I sine 0. Cosine 0 is 1, as I know all of you know by now, plus 0i. This is just our good friend 1 here, right? So that's for k equals 0. Let's see what happens when k is equal to 1, and the producers just told me I have a minute and I better hurry up, or there's going to be a beating in it for me. This is going to be cosine 2 pi over 2 plus I sine 2 pi over 2. This gives us cosine pi plus I sine pi. This is -1. We'll be right back.